Introduction to the definite integral. As you recall, in the sections we covered previously, we delved into the world of indefinite integrals. We spent time understanding what integration is, and a key idea we established was that integration is fundamentally the reverse operation of differentiation. If differentiation tells us how a function changes, integration helps us find the original function, or more accurately, a family of functions that could have produced that change. Now we're building on that foundation. Up until now, when we integrated a function, we obtained a general formula, a function plus a constant, representing an infinite number of possible antiderivatives. But in this section, we're shifting gears. We're no longer interested in finding a general family of functions. Instead, we want to calculate a specific numerical value. Think of it like this. We're going from finding a recipe that could make many cakes to actually baking one specific cake and determining its exact weight. That transition, from a general formula to a specific number, is precisely what the definite integral allows us to do. This numerical value often represents an accumulation of a quantity, or geometrically, the area under a curve, but we'll explore those ideas in more detail as we move forward. So, this is the core concept behind the definite integral, and we'll unpack it step by step in the following slides. Okay, so let's begin our discussion on the definite integral. Understanding the concept. First, let's recap what an indefinite integral gives us. An indefinite integral provides a general formula for the antiderivative of a function. So, if we integrate a function which we're calling f of x, we don't get a single function back. Instead, we get a family of functions, represented as f of x plus c, where c is the constant of integration. Remember, c is there because the derivative of any constant is 0, meaning many functions could have the same derivative. This f of x plus c represents a whole family of curves. Think of it as a general pattern. Now, a definite integral is different. It's calculated over a specific interval. This is a crucial distinction. Instead of giving us another function, a definite integral gives us a single, unique numerical value. It's a number, not a formula. And what does this number mean? Well, geometrically, if our function f of x is positive, the definite integral represents the net area under the curve of that function between two specific points on the x-axis. We'll explore how to calculate this area in the upcoming slides, but for now, it's important to grasp that we're moving from finding a general family of functions to finding a specific area, a specific number. This concept of net area is important, as areas below the x-axis are considered negative, and we're finding the net effect of all the areas. Okay, so let's move on to understanding the core concept of the definite integral. As we discussed on the previous slide, we've already explored indefinite integrals, essentially finding the reverse of differentiation. Now, we're going to see how that changes when we want a specific answer, rather than a general formula. So keep this difference in mind. Indefinite integral, a family of functions; definite integral, a single number representing an area or accumulation. We'll build on this understanding as we go through the rest of the tutorial. Notation of the definite integral. Okay, so now that we've discussed the core idea of definite integrals, moving from finding a general function to a specific value, let's look at how we actually write it mathematically. This slide introduces the notation for the definite integral. Here we have, the definite integral is represented by the following mathematical notation. And what you see here is the symbol we use, integral from a to b of f of x with respect to x. Let's break this down piece by piece, because each part has a specific meaning. First, we have this elongated S shape. That's the integral symbol. It essentially tells us that we're performing an integration operation. Next, we have f of x. This is the function we want to integrate. We call this the integrand. Think of it as the thing we're finding the integral of. Then we have dx. This little piece is crucial. The dx tells us with respect to which variable we are integrating. In this case, we're integrating with respect to x. It signifies that we're considering infinitesimally small changes in x. Now let's look at the limits of integration. We have a at the bottom and b at the top. A represents the lower limit of integration. It's the starting point of our interval. And b is the upper limit of integration. It's where we stop integrating. These limits define the specific interval over which we're calculating the definite integral. So, putting it all together, the expression integral from a to b of f of x, with respect to x, is read as the integral of f of x from a to b. Remember from the previous slides, this isn't giving us a function anymore, it's giving us a number. And these limits, a and b, are what allow us to get that specific numerical value. In the next slide, we'll really highlight the differences between definite and indefinite integrals, so understanding this notation is key. Definite versus indefinite integrals, key differences. Okay, let's move on to slide 4. As we've discussed in the previous slides, both indefinite and definite integrals are powerful tools, but they serve different purposes and have distinct characteristics. This slide neatly summarizes those key differences in a table format, which will help solidify your understanding. Let's start with the first row, looking at the result. For an indefinite integral, remember we're finding a family of functions that have the same derivative. So, the result is a general function. We always add plus c, the constant of integration, because infinitely many functions can have the same derivative. However, a definite integral, as we've started to see, gives us a specific number, a single numerical value. Think of it as a constant, not a function. Now let's look at limits. With indefinite integrals, we don't specify any boundaries or limits on the integration. We're finding the most general antiderivative. But with a definite integral, we always have a lower limit, which we denote as a, and an upper limit, denoted as b. These limits define the interval over which we're calculating the integral. Moving on to the constant of integration. As we just mentioned, the indefinite integral always includes the constant c because of the nature of finding antiderivatives. However, and this is crucial, the definite integral does not include the constant c. Why? Because when we evaluate the definite integral, that is, when we find the difference in the antiderivative at the upper and lower limits, the c terms actually cancel each other out. Finally, let's consider the purpose. The main goal of an indefinite integral is to find the antiderivative of a function. It answers the question, what function, when differentiated, gives me this function? On the other hand, the definite integral is used to find the net area under the curve of a function between those limits, a and b, or more generally, to find the total accumulation of a quantity over that interval. We'll explore these applications further in the upcoming slides, particularly with the example of distance and velocity. So, to recap, this table provides a clear side-by-side comparison. Keep this slide in mind as we move forward, as understanding these differences is fundamental to mastering definite integrals. Real-world example, distance and velocity. Okay, let's move on to a real-world example to really solidify the difference between indefinite and definite integrals. This slide uses a scenario many of us can relate to: a car moving along a straight road. Let's consider scenario A, indefinite integral. Imagine we know the velocity function of the car, which we'll call v of t. If we take the indefinite integral of this velocity function, that's the integral symbol followed by v of t and then dt, we get the general position function of the car, which we'll denote as of t plus a constant c. Think about what that constant c represents. It's the initial position of the car. We only know how much the car has moved from a certain point, not its absolute location, unless we know where it started. So, the indefinite integral gives us a formula for the car's position, but it's not a specific location without knowing that initial condition, c. Now let's look at scenario B, definite integral. Suppose we don't want to know the general position, but instead we want to know the total distance the car traveled between, say, the second and the fifth second. This is where the definite integral comes in. We would set up the definite integral as follows: the integral symbol, then the velocity function, v of t, then dt. But now we add limits of integration, a lower limit of 2 and an upper limit of 5. So it looks like this. The integral from 2 to 5 of v of t dt, this integral calculates the area under the velocity curve between the second and fifth seconds, and that area directly corresponds to the distance traveled during that specific time interval. Notice we don't have a plus c here. The limits of integration take care of giving us a single numerical answer, the total distance traveled. Now, remember from the previous slides, an indefinite integral gives us a family of functions, while a definite integral gives us a specific number. This example will illustrate that beautifully. In the next slide, we'll break down exactly how to calculate this definite integral step by step. But this example should give you a good intuitive understanding of why we need both indefinite and definite integrals, and what each one tells us. Step-by-step breakdown of the calculation process. Okay, let's break down how we actually calculate a definite integral. This slide outlines the step-by-step process, building on everything we've discussed so far, remembering that unlike indefinite integrals, we're aiming for a single number as our answer. Step 1, identify the function. This might seem obvious, but it's crucial. We start with the function we want to integrate. In our running example, we're using the velocity function, which we're calling v of t. So, we clearly identify what f of x is in our notation. In this case, it's v of t. Step 2, set the boundaries. Remember from earlier slides that the a and b in our integral notation represent the limits of integration? Well, here we define those. We're given a specific interval from the second second to the fifth second. So our lower limit, a, is 2, and our upper limit, b, is 5. These values tell us where on the x-axis, or in this case, the time axis, we're calculating the area under the curve. Step 3, integrate. This is where our knowledge of indefinite integrals comes in handy. We need to find the antiderivative of our function, v of t. Finding the antiderivative essentially reverses the process of differentiation. So, we apply the rules of integration we learned earlier to find a function. Let's call it sub t, such that the derivative of sub t is equal to v of t. Don't worry about adding plus c, the constant of integration at this stage. We won't need it for definite integrals, as we'll see. Step 4, evaluate. This is the key step that turns the antiderivative into a number. We now take our antiderivative, sub t, and evaluate it at both the upper and lower limits of integration. That means we calculate sub 5, the value of the antiderivative at t equals 5, and sub 2, the value of the antiderivative at t equals 2. Then, we subtract the value at the lower limit from the value at the upper limit, sub 5 minus sub 2. This subtraction is what gives us the definite numerical value. Step 5, result. And finally, the result. After performing the subtraction in step 4, we're left with a single number. In our example, let's say that number is 50. And importantly, remember to include the units. Since our velocity was in meters per second and our time was in seconds, our result, 50, represents 50 meters, the actual distance the car traveled between the second and fifth seconds. So, to recap, we go from a function to an antiderivative, and then to a single numerical value representing the accumulation of the quantity over that specific interval. This process will be crucial as we move forward and apply definite integrals to more complex problems. Key takeaways. Firstly, remember that a definite integral doesn't give you a function like the indefinite integral does. Instead, it always results in a unique numerical value, a single number. Think of it as a final answer, not a formula for a family of functions. Next, let's look at the notation. We write a definite integral as integral, and then we have a function, f of x, and then dx. This is all with limits of integration. The integral symbol, followed by the function we're integrating, f of x and dx, which tells us we're integrating with respect to the variable x. Crucially, we have a lower limit, a, and an upper limit, b, written as subscripts around the integral symbol. So, we read this as the integral of f of x from a to b. This notation clearly defines the interval, from a to b, over which we are calculating the integral. It's telling us exactly where on the x-axis we're interested in finding the area or accumulation. Now, a really important difference from indefinite integrals. You do not need to add the constant of integration, c, when evaluating a definite integral. Remember, with indefinite integrals, we always added plus c because there were infinitely many antiderivatives. But with definite integrals, because we're looking at a specific interval, that constant c always cancels out when we evaluate the antiderivative at the upper and lower limits. So, we leave it out. Finally, and this is a core concept, a definite integral represents the accumulation of a quantity. It could be distance traveled, as we saw with the car example. Or, geometrically, it represents the net area under the curve of the function, f of x, between the points a and b on the x-axis. Keep this idea of accumulation in mind, as it will be more useful as we move forward and apply definite integrals to more complex problems. Okay, let's recap the key takeaways from definite integrals. As we've discussed, moving from indefinite to definite integrals is a big shift in what we're doing with integration. In the next slide, we'll look at some common mistakes students make when working with definite integrals, so it's good to have these key takeaways firmly in your mind first. Common mistakes to avoid. Okay, so this is our final slide, and it's really important because it highlights some common pitfalls students encounter when first learning about definite integrals. Let's go through each of these mistakes one by one so you can avoid them. 1. Adding the constant c dollar. Now, remember when we were working with indefinite integrals, we always added plus c to the end, representing the constant of integration. Well, with definite integrals, that changes. A lot of students, out of habit, still add plus c even when calculating a definite integral. But don't. When you evaluate a definite integral, you're essentially finding the difference between the antiderivative at the upper and lower limits. Because of this subtraction, the plus c terms always cancel out. So, the final answer you get from a definite integral is a numerical value, a constant, and doesn't need the c. 2. Confusing the limits. This one's about carefulness. The notation for a definite integral is integral with the lower limit, a at the bottom and the upper limit, b at the top. Integrating a function f of x with respect to x, it's crucial to get those limits in the correct order. If you swap them, put b on the bottom and a on top, you're not wrong in the sense that you'll still get a value, but that value will be the negative of the correct answer. Mathematically, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. So, always double-check that your lower limit is indeed at the bottom and your upper limit is at the top. 3. Treating it as a function. This is a conceptual mistake. Remember, the indefinite integral gives you a family of functions, right? But the definite integral, after you apply those limits of integration, gives you a number. It's a specific value. So don't think of the result of integral from a to b of f of x dx as a function of x once you've evaluated it. The variable x disappears, and you're left with a constant. It represents a quantity, like distance traveled or area, and that quantity is a fixed number, not a function that changes with x. So keep these 3 points in mind, and you'll be well on your way to mastering definite integrals. Are there any questions about these common mistakes?